So we're going to look at a recursive relationship now. And what we're interested in is we want to know what the value of the stand is at any given state I with t periods until the end of the time horizon. Now notice that we have this beta, which is our discount factor, is 1 divided by 1 plus r to the power 20. And if I let if I let the interest rate, r, the discount rate, be 5%, then what this turns out to be is that beta equals 3.377 if r is equal to 5%. So we're going to use that number throughout, so keep that in mind. The present value of expected returns with t plus 1 periods to go to the end of the time horizon is given by the immediate return if you're in that state. So if you're in the low state, you got no return, it's 0. The medium state, 0. But the high state, we earn 7,254. Then what happens is we discount, we use that discount factor, and we determine what the previous year was in state L, what the value was if it was in state M, and the value if it was in state H. These values here tell me what the probability is that if I'm in current state I, that I'll be in the low state next period, so in 20 years from now. So if I'm in the low state now, and I want to know what the probability is that I'm staying in the low state, I go back to that transition probability matrix, and I think it was 40%. And we do the same thing for the medium and the high states as well, and I'll give an example in a moment. But we begin with, notice that this is our transversality condition, if you like, and it tells us that at the end of the number of periods that we consider, that or the stand has no value. You can change that. You can make these numbers be some value and then work the problem backwards. So when we begin with this particular result here, that everything is 0, these numbers will all be 0 to begin with. So then we go to the first stage, and we assume that discount rate of 5%, and you'll notice here that I have that 0.37. So if we're in the low state, the immediate return is 0, but the return down the road is given by, and I'm using the old version of this to calculate this, the old transition matrix, and we find that we have all these zeros, so in effect, because of that 0, everything is 0. The same thing if we're in the medium state, everything is 0. If we're in the next state, the highest, we get this immediate return, and as a result, this is what we're going to get. So for the next state, so if we replace that VH0 with VH1, we'll put this number 7254 into that VH1 category. And we'll do that there, here, and here. All right? So you got to be careful. Now in stage 2, we would then, keeping the same, and I may have to just keep that the way it is in that PDF. I'll leave it the way it is for now. We find that the second period, we got that number there, so we get that return. So we multiply 7254 by 0.1 and then by 0.377. The others are all 0. So these are zeros, and we end up with 217.62. We do the same thing here. Notice that 7254, we had a 75%, and we're going to have 2,5107. And likewise down here we get 7254 back again, because the probability of being in the high state and staying there, given that we got the 5 and the 0.5 here. And I guess I'm not going to change the PDF because, will not change PDF, because what I have here is enough information. I'd have to change all of this down, and we're going to look at this a little bit later on in a bit more detail. Okay, so now we continue to stage 3, and we work it the same way as we did before. We're going to get that 7254 here, but now we have this 2005-1 to look into, and that one shows up in the middle. All right, here it is again, 7254 here again, and so on. There again, and again, and again. And where does this one come from? Well, that comes from up here. Okay. So if we go through this whole recursive relationship, then in stage n, since beta is less than 1, 0.377, convergence eventually occurs. In this case, it converges at greater than 10 time periods. And when we look at that, we find that these are the values that that we end up with. This is if we're initially in state L, then if we follow this optimal program, we're going to earn $624 per hectare by year 10. If we are in medium state, we're going to get $23.43, and if we're in a high state, we're going to get $78.78. The long run expected return is found by multiplying the above values by your probabilities of being in each of these states, and in this case we get $3,736 per hectare. Now, so far we've not made any decisions, all right? So what we're going to do, all right, all we've looked at here is if we manage the system according to this particular these particular, and I'm going to get rid of this for now. It'll show up anyway on the video. If we use this particular transition probability matrix, then we will get exactly these results, we will get these results, and we will end up through this recursive relationship, we will end up with this result down here. All right, and the mean or expected return would be that amount. Now, we haven't made any decisions yet. So with stochastic dynamic programming, we want to make a decision. So we're going to let Pij k be the probability that if the system is in state I, at time t, it'll be in state j at time t plus 1 if we choose a decision variable k. So we can write this as Bellman's equation as the value at any given time, given a particular state variable, what state the forest is in, low, medium, or high, and given a particular choice variable, ut, or if you like, the harvest, then we end up with wanting to maximize the choice of harvests, which give us an immediate return plus a discounted value of future returns. So it assumes that in the future we make optimal decisions, and we can rewrite this particular component of it as follows. So first we have maximize with respect to k, make the right choice of k. This is our expected return given I and given choice k. And then given that we make that decision, we also get a future, and if we follow the future and make optimal decisions in the future, choosing k optimally in the future, then we will be able to determine what is the optimal choice today. So we can rewrite that as maximize the decision at given time t is given by the expected return for that decision plus the expectation of what that decision means for the future. So this here is the future, and the future is chosen in a way that we maximize everything. So what we're going to do is we're going to look at how this works. So we have transition probabilities replace, so these transition probabilities replace the state equation, or what we've sometimes referred to as the equation of motion. And we can write this as the state equation, the transition probability. If we have choice U1, if we make that, we have, these are the probabilities for choosing 1. These are the probabilities for choosing 2, for making the second choice. So in one case, we may choose to harvest a certain amount. In another case, harvest a different amount, and we get a probability distribution for each of these. One transition matrix is required for each decision, and that is often a problem. One transition matrix is required for each decision. So if you have a lot of decision possibilities, then you have a lot of these transition matrices. You can have 5, 6, 7, 10, depending on decisions. Remember when we were working with phase plane diagrams, we basically had the same thing, but then the harvest decision was based on a continuous scale, but all we could do is harvest. We couldn't say, okay, we're going to harvest plus we're going to then also fertilize, and how much fertilizer and when to fertilize were not decisions that you could make with those phase plane diagram kind of models. So the thing to note about these probability transition matrices is that the sum of each row has to be 1. Well, that's obvious. All right, when you transition from say from the low state to the medium, you have either you transition to the low state here, you stay in the low state, or you go to the medium state, or you go to the high state. There are no other possibilities, and you have to have the sum of those probabilities across that line equal to 1.0, because there are no other possibilities. The other more important thing here, or less obvious, is that the columns have to be single peaked. That means that the probabilities, so 0.2, 0.3, and then 0.5, that's single peaked. The peak is here. You might have something like this, 0.5, 0.3. There again, you have a single peak occurring here. You can't have 0.3, 0.1, 0.3. because you don't have a single peak. It's not peaked here, it's got 2 of them. So that gets a little more complicated. And we have this Markov assumption, and the Markov assumption simply states that all the information about the past is contained in the present value of the state variable. So all of the information, and I mentioned that a little bit earlier. Now, we have various things to discuss here. First of all, policy iteration. We want to look at how we might solve these kind of problems. If any state is reachable, this is a key part of this particular kind of modeling, this kind of optimization, is that any state has to be reachable from any other state. If that's the case, then there is convergence towards an optimal policy that holds for any time t. All right, there's a convergence of any optimal policy that holds for any time t. So in the past, what we've done is we've modeled soil moisture, for example, and that leads to policy iteration. So your soil moisture at one time could be in a high state and then drop to a low state, but it can get back into a high state through for example, precipitation, snowfall, or whatever. But the moment we introduced soil depth as a second state variable, so you have soil depth and soil moisture, your soil depth declines over time. It doesn't come back. So if that's the case, if it doesn't come back, that means that if you're in a state where you have 2 meters of soil, and you drop to 1 meter of soil, you can't get back to 2 meters of soil. In that case, you have to use what's called value iteration, because the optimal policy depends not only on the value of the state variable, but also on time. So on time, the soil erosion occurs, and as a result, some states are not reachable from any other state. And there can be an absorbing state. So for example, in the soil erosion, you might have an absorbing state where you have less than 5 inches of topsoil. Another absorbing state would be the case of a firm that goes bankrupt. That's an absorbing state. The other thing that we define here is this optimal policy, an optimal decision for any value of the state variable at any time t. So we have two methods of solution, a policy iteration and a value iteration. And the way they work is with policy iteration, you end up solving the problem for all time. In other words, once you have a solution, that's going to hold irregardless of what time period you're in. With value iteration, you have to run the model and it continues basically forever, but it changes over time. So in other words, the decision you make in a low state and in a high state are going to differ today from what they were yesterday or the day before. So for example, with the soil moisture, that's a clear example where things are all reachable. With climate change, for example, the argument is that things are not reachable. Once you've hit these high temperatures, you can't go back, kind of thing. All right, here are the corrected transition probability matrices that we're going to use from now on. So I'm not going to change the PDF as I mentioned earlier, but I'm going to use these for the current work. So you notice here that if I don't cut the trees, I have a probability that I'm in the low state. I'm 40% chance I'll remain there, 60% chance I'll be in the medium state. I use the same probabilities here if I do cut the forest. If I'm in the medium state, I'm going to use that I'm going to stay 40% chance that I'm in the medium state, 60% chance that I get into the high state. I've reduced that a little bit here, but it makes very little difference. But I did want to show that this medium state was different than the one for the cut compared to the one for the no cut. And then finally, if I'm in a high state, there's that 5% chance that I go to a low state or a medium state due to natural disturbance, and 90% chance that I stay in the high state if I don't do anything. I don't manage the stand, I don't cut it or anything like that. If I cut it, there's a 90% chance that because I drop to a low state that I stay there, but a 10% chance that I still manage to get within those 20 years into a medium state, and there's no way I'm going to be in a high state. Returns to each decision state, we're going to just pick a couple of returns. We're not going to make it dependent on how much timber is on the stand. We're going to say that you get, if you cut it, you get $472 if you're in a medium state, and if you're in a high state, you're going to cut and get $72.54. Now, right off the bat, you should be able to figure out that it's unlikely that with these numbers and with a discount rate of 5% and with a 20-year time step, that people who have a forest in the medium category are going to actually let it grow to the high category. They'll probably cut the trees before then. So that's just a gut feeling here that that's what will happen. All right, we're going to look at that recursive relationship, the present value of expected returns with t+1 periods to go to the end of the time horizon. So we're going to start with this equation. This is our Bellman equation here. We have two decision variables, cut or no cut. So this is the no cut, and this is the decision if you cut. Okay, so what you have to do is you're going to pick the maximum of this number. So either this number or this number. All right, either this number or this number, whichever is highest. And Pijk here is the probability that a stand moves from state I to state J when the decision is K. Recursive relationship, we proceed as before, but now keep track of the best decision. We're going to keep track of these decisions as we go along. Again, we're going to begin with 0 value. So our endpoint value is 0, that the stand is not worthless. We're going to use 5% discounting, so the beta is 0.377, the discount factor. And now we're going to actually do this. So when we start in the low state, we're going to maximize. There's no value in the low state, and there's no values here for next period because there is none. So if we look at the terminal value, we've already decided up above that those terminal values are 0. Where is that now? Here we go. No, terminal values, I can't find it right off the bat. But the terminal values, oh, here it is, are 0. So that's why we have these zeros here. And this tells us that there's a 40% chance if we're in the low state that we're going to end up in the low state, and a 60% chance that we'll be in the medium state. So when we maximize this, what do we get? Well, we get 0 here. If we're in the medium state, we do the same thing, but now we've got 4,472 is our current. So I've marked in red the current revenue or expected revenue. And here again, we have these zeros. So notice here that in the medium state, you're going to earn 4,472. And now if we go to the high state, we find the same thing, 7,254. And these again are zeros. So now we go to the second state. So the first state was no cut, cut, cut. Stage 2, we're going to have that 0 again here. So we're in the low state. Notice here that I've got 4,472 and a 60% chance in both cases. And here's 7,254, but the 0 probability that you're going to be in that high state to get it after you've cut in the low state, or even if you leave it unmanaged in the low state. So these two values are identical, and they're equal to 10, 11, 57, and the choice is not to cut. We go to the medium stage, and again we have these 4472, 7254 in these categories, and 4472 is what we get as an immediate return, just as we did before in stage 1. See, here's our stage 1 numbers and the probability that we would be in stage 1, given that we're in medium stage now. The future probability of being in that stage are 0.35, or in the higher stage 0.65. Here they're 0.4 and 0.6. And if we compare these two numbers, I haven't put that number down, but it's less than this number. So this is the choice because it leads to the bigger number, 0.65 times 724, and that, but it's this number that's driving it. So we end up with 6839.67, and we'd cut it. If we're in the high state, we have an immediate return if we cut it of 7254. 4472 is if we're in the medium state. There's a 5% chance that we're in there given we're in a high state, but we're not cutting. A 10% chance if we cut and we're in the high state that we'd be in this middle state. And 0% chance here that we'd be in the high state, but here it's 90% chance. So if we multiply 7254 by 0.9, then by 0.37, we get a smaller number than this number plus 0.377 times 0.1 times 4472. In fact, the number we get is 742259, and the decision in this case is also to cut. Stage 3, if we go to stage 3, period 4 in what's going to follow, then you have precisely the same procedure. Using a computer program that solves the forest management stochastic dynamic programming problem, or also known as the Markov chain programming problem here, one gets the following returns. All right? And the optimal strategy over all time is to not cut, not manage in the very first low state, and then manage in both the states thereafter. And here's what happens. You can see what happens here if I run this computer program. Here, these numbers were the same as the ones I calculated by hand up above, or very, very close. And then you can see that you don't want to be doing this by hand, particularly if the problem is even bigger. You can do it by hand for this particular problem, but it is a bit of work and a lot of calculations. The computer does this in under 2 seconds. And what happens is, notice the convergence here. After about period 12, we're converting on eventually these numbers here. What is that? Why does it do that? Well, very simply because of the discount rate. When you're 20 periods out, think of that, 20 periods times 20 years, 400 years out. By then, you're not going to, anything you do in 400 years out has no impact in terms of today's present value. Now, we want to look at the long-run solution. So after 20 iterations, the algorithm converges on an equilibrium solution, as shown here. And what we find is that the net present value of that solution, I'm just putting these numbers down here, is 1989, 7469, and 8210. No cut when you're in the low state, cut in the medium, and cut in the high. And the long-run probabilities are that you're going to be 37% chance in the low state, 38% chance in the medium, and a 25% chance in the high state. Now, how do we find the long-run probability vector and expected returns? Well, we create a new transition matrix, and this is the key. We're going to create a new transition matrix by taking, for each decision, the row associated with that decision. So if we go back to this decision, the decision was to cut if you're in the medium or high states, and not to cut if you were in the low state. So you go back to the probability transition matrix between the two, and let me just check that quickly. Okay, so what we'll do is we're going to take this vector here, and we're going to combine it with this part of the matrix. So we're going to stack this on top of the other one to get our long-run probability transition matrix, because our choice is to not cut whenever you're in this low state, and to cut whenever you're in a medium or a high state. So we take this for these two vectors, if you like, and we're going to stack this other vector above it, and that's going to be our long-run transition probability matrix. Now notice that this 0.4 and 0.6 here are the same, which is just a coincidence. It doesn't necessarily have to be that way, but the idea is to take that vector and stack it on top of that one. Okay, let's go back now to where we're calculating these things. So that once we've created that new transition probability matrix, so suppose that the transition matrices are, we have to assume they're reachable, and that the optimal policy is mu1 if in state 2 and mu2 when in state 1 or 3. So this is a bit contrived. This isn't exactly like it was above. Well, we pull out, you see, we pull out the second here and the first for this one. So this is basically how that's done. In our case, it's a little bit different because we only have that we have the low, and then stack the medium and the high. They come from the cut matrix, and the low comes from the no cut matrix that we showed above. And we're going to let pi 1, pi 2, pi 3 be the probabilities of being in states 1, 2, and 3 in the long run. So these are the probabilities of being in states 1, 2, and 3 in the long run. We can solve pi, as was done earlier, by solving this particular equation. There's a problem solving that, even though when you are able to solve that, the limit as n goes to infinity of p to the n gives you this exact result. In other words, the matrix will consist of rows that are identical. So they're identical rows. That's a key. However, if I take that p to the n and I multiply it by itself, what am I going to get? Well, I'm going to get a big fat zero matrix, because the p's, all of these numbers here, in here, are all less than 1. And if I multiply, let's say, 0.1 times 0.2, I get 0.02. And if I multiply that by 0.1, I get 0.002, and so on. And as a result, the thing collapses all the way into 0. So the probability, or the problem is that since probabilities have the property that they're less than or equal to 1 and greater than 0, as n approaches infinity, p collapses to a null matrix. So a different approach is needed. So we can find that pi matrix, that pi vector, pardon me, by first introducing an identity matrix and a matrix D, where there's a column of 1s at the very end, and we take these probabilities, this probability where they're all identical, and we can get that using this formula here. D times the inverse of I plus D minus P. Then the expected returns are, we just choose any row of big pi, and that is the probabilities of being in low, medium, or high in the long run. We multiply that by the expected returns for being in low, high, medium, and high. And as a result, we can then find our expected return. So in the previous cut no harvest timber management example, the decision rule is no cut whenever in state L and cut in states M and H. So we take that low L row from the no cut matrix and the M and H rows from the cut matrix, as I pointed out above, and we get this matrix here. This is our long run transition probability matrix. We then calculate I plus D minus P, which gives that. We then calculate the inverse of that, which is this, and we multiply that or pre-multiply it by D, and we come to this result. Notice that each of these rows is identical, so we can pick any one of those rows, and that then is our pi. So from the stochastic dynamic programming algorithm, ignore this part here a minute, the long run expected returns for each state are as we showed above. The long run expected return is found by multiplying the pi vector by the returns vector, which gives an expected return of about $3,500 per hectare with a standard deviation of about $2,900. Note that you never let the trees grow to reach state H because you harvest them in state M. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.